Okay, welcome everyone. It is a great pleasure to introduce our speaker today. He is César Zapata, who is coming from Brazil, the University of Sao Paulo. And César will be talking about the higher topological complexity of maps. Please, César.
Okay, thank you very much. Hello, everyone. It is a pleasure to present this talk. Okay, and this is a joint work with Jesus Gonzalez. Okay, I will present. Just 1 minute. Okay, I will present the initial motivation problem for this. How or why we introduce this new numerical invariant. Okay, and for example, you have this robot here, and you consider another object, for example, as an obstacle. Okay, the classical problem, motion planning problem, is how to find or design an algorithm. For example, in this case, the input for that algorithm is the initial position for this and for a star decider position. But in this case, this robot, we ask to pass for this intermediate intermediate position. Okay, in this case, we want to move this robot from R1, R2, R3, and finally R4. This obstacle is a mobile obstacle, okay, but in the input of that algorithm, we don't input the initial position of this obstacle, only for this robot, okay? And how to decide or how is the complexity for this problem, we will see later that the complexity is 1, okay? But this is a particular situation, okay? I will change, okay, a little for this situation. For example, now we ask or we looking for an algorithm, but the input is the initial position of our robot and initial position for this obstacle. The other, then also in again the robot for this 1, 2, R2, R3, and finally R4. Okay, the difference is that in the input of this algorithm for this problem is the initial positions, okay, for this obstacle. Okay, a big change is now I will input in that algorithm initial position of the robot, initial position of the obstacles, then second position for the robot, and second position for the obstacle, then 3 position for the robot, and the obstacle, the 3 and the 4 position is not input in that algorithm, only the 3 position of the robot and the 4 positions of the robot. Okay. With the previous one, this complexity for this problem is not 1. Okay, I will see that the complexity is 2 for this case. Okay, and if now in the input of that algorithm we input that initial 2 intermediate position for the both obstacle and robot, but in the last step, we are not interested in the final position, okay, for that obstacle, only for the robot. Okay, we will see that the complexity for this situation is 3. Okay, and how to study in the setting of topological complexity this problem is the motivation to introduce the higher topological complexity. Okay, this new numerical invariants, okay, generalize in particular Rudyak's higher TC, okay, the Pavesic topological complexity for a map, okay. Moreover, this numerical invariant unifies another invariants, for example, Rudyak's summing higher TC, Murillo-Gus topological complexity in the higher settings, and the Scott topological complexity in the higher settings. Okay, this numerical invariant coincides with this when F admits a section, F is a map, and S equal R. Okay, this new numerical invariant unifies all of them. Okay. Moreover, if F is a vibration with section, okay, then this TCRR coincides with TCRR minus 1 and coincides with the higher TC of Rudyak's. Okay, this is the motivation, okay, for this work. I will present some generalization, okay, but before that, I will present some preliminaries. Okay, for example, the classical sectional number and the classical sectional category. Okay. Okay. We recall that sectional number is the minimum number, okay, when B admits an open cover with K open success, okay, such that each over each admits a local session to this map phi. Okay, this is the sectional number. Similarly, the sectional category, this is not a strict section. This is a homotopy section. Okay. Yeah. I will recall a previous version of TC. Okay, for example, the Pavesic TC. Okay, for any map, the Pavesic topological complexity for the map is the sectional number of this map here. Okay, this map is the composition of the double path vibrations, okay, which define the classical Farber topological complexity, okay, and composite with identity times F, okay. The sectional number of this composition, Pavesic calls complexity of F, okay. And before to introduce or to recall the Murillo-Gus topological complexity, I need to introduce this numerical invariant, okay? And the sectional, the C, here C is a map from B to C, and phi is a map from A to B. The C topological complexity of phi, okay, is the minimum number such that B admits an open covering, okay, and in which admits a map from BG to A such that this composition, okay, is equal this restriction map. Okay. Similarly, the C sectional category, okay, but this is not a strict equality. This is okay at a homotopy. Okay. With these numerical invariants, okay, we recall the Murillo-Gus topological complexity. Okay, given a map F, the Murillo-Gus topological complexity is the sectional category of this map. Okay, the F sectional category of this map. Okay, in the previous sense. And also, Murillo and Gus define the naive or strict topological complexity. Okay.
Cesar, in the previous slide, I think you want, the map is in there. The map is 1 cross F or F cross F.
I'm sorry, in the previous.
That one. No, next one.
Okay,
There.
here.
There. Just stop.
The next.
Stop.
Okay.
Just leave one. That one. Leave it. You see, you have F cross F. Do you want?
Yeah. Okay. Yes. Yeah. This is a mistake here. This is Y. Okay. I'm sorry.
Thank you.
This is Y. Yes. Thank you. Let's change here. It's Y times Y. Okay. Okay. The Murillo-Wu topological complexity is the F times F sectional category of this vibration. Similarly, the naive or strict topological complexity in the sense of Murillo and Wu is the F times F sectional number of this vibration. Okay. And then I will recall that relative sectional number. Okay. Here we consider a map. Okay, two maps. Okay. And we consider the pullback, the canonical pullback. The relative sectional number of 8 with respect to G, okay, is the sectional number of the canonical pullback. Okay, this is the relative sectional number. And with this, Scott, okay, introduce the TC, okay, giving a map, okay, we consider this part vibration, okay, we consider F times F here, and the Scott topological complexity of F is, okay, the relative sectional number of this vibration with respect to this product, okay. And Rudyak and Somen, okay, defines a notion of higher TC for a map, okay. They use this new numerical variant and they call quasi-strong category for a map, okay. Here we consider a map from A to a space B and we consider a subspace C in B, okay. The quasi-strong category for 8 is the minimum number such that 8 admits an open covering, okay, such that this restriction map is homotopic for a sun map which image in C. Okay, this is called a strong, quasi-strong category for a map. Okay, with this, they defined. Okay, I will present then that is, I'm sorry, I forgot this. Okay, okay, this. Giving a map, okay, and R more or equal to the Rudyak assessment higher TC is the quasi-strong category for this product, okay. Here is with respect the diagonal subspace, okay. Well, I will introduce in particular or higher TC and other higher TC for the previous one. Okay, for example, or higher TC is very natural. Okay, we consider a map F. Okay, and integer at more or equal to and S between 1 and R. Okay, here we consider the space. Okay, this is the union of the interval 0, 1. Okay, when we identified, okay, the 0. Okay, and this is the set multipath here. Okay, the space of the multipath, okay, in X, and we consider this this path vibration. Okay. Recall that the sectional category of this map is the higher topological complexity of Rudyaks. Okay, we consider here composition with this product. Okay, here the identity times Fs. Okay, this map we denote by A up F, R, comma S. Okay, and we define the topological complexity Rs of F by sectional number of this composition. Okay, in the homotopy setting, we define the homotopy hierarchy of F, okay, by the sectional category of this map. Okay, and so natural remap is when F is the identity, okay, coincides with the Rudyak TC. Okay, and when R is 2 and S is 1, they coincide with the complexity of Pavesic complexity. Okay, and moreover, we have this, okay, this property for any map, okay, if R, okay, compare with this, the monotonic property of or invariant, okay, that's happening this, okay. R is less or equal the complexity for x plus 1, but S is fixed, okay, or if you increase R and S simultaneously, and the complexity is bigger, okay. Okay, and I will introduce the RS quasi-strong hierarchy C, okay, which is a natural generalization, okay, for Rudyak and so TC. Okay, for S between 2 and R, we consider this product. Okay, this is the YR times R minus S times this diagonal. Okay, and we define the quasi-R as quasi-strong hierarchy C of F by the quasi-strong category for this map with respect to this, okay, subspace this, okay. A natural remap is when S equals R, that coincides with the Rudyak and Schumann topological complexity. Okay. Then I will introduce also the Farber-Murillo topological complexity. Okay. Again, S is between 1 and R is more or equal to, okay. The Farber-Murillo topological complexity is this product of the sectional category with respect to this product, okay, of this vibration, okay. And similarly, the naive Murillo-Sangu hierarchy C, okay, is the identity times Fs sectional of this vibration, okay. This is a natural remap and will notation. I will denote, okay, when S equals R, okay, by TC Murillo RF, okay. Similarly for the strict TC, okay. And note that when R equals 2, and that it coincides with the Murillo's TC, okay. A natural generalization of Scott TC is considered for any R more or equal to the hierarchy TC of Scott is the sectional number of the relative sectional number of this vibration with respect to this product. Okay, for R equal to coincides with the Scott TC. Okay. And now a general proposition for all invariant is this, okay? For any map F, we have these natural lower bounds, okay? This is for any S less than R, and this is for the case S equal R. Okay, we have this lower bound for all this, Okay, this is lower bound is very natural. Okay, and an upper bound is this in terms of the Murillo's and Wu hierarchies. Okay, and as a corollary, we have that when X is contractible, okay, then or hierarchy C coincide with the sectional number of Fs and which coincide with the category of Yx. Okay, here is an example in which the dependence of S, okay, is clear. Okay, and then we compare, okay, or TC with the higher of the previous one. Okay, for any map F and for any R at least 2 or equal to, we have that Rudyak's summand higher TC and Murillo's higher TC and Scott higher TC, all of them coincide and then are lower bound for all homotopy TC R, R. Okay. In addition, if F admits a section, all of them coincide. Okay. Moreover, coincide with the Rudyak TC. Okay. This statement, okay, shows that all invariance is a unification, okay, for the previous higher TC. Okay. And moreover, we have this estimate, okay, for general, okay, for all higher TC, okay. This inequality is called for any map F, okay, with session, okay, for any map with session, and or higher TC, okay, is between the Rudyak TC of the domain, okay, and the Rudyak TC, okay, of the domain, okay, is between them, okay. It is also possible to show that or TC in this case coincide with the higher Murillo's and Wu TC, okay. And in that case, when F is a vibration, we obtain, okay, new estimates, okay. For example, in a case when S is equal R minus 1, okay, the topological complexity of F is less or equal the Rudyak TC of the domain. In addition, if S admits a section, okay, we have this the equality holds. Okay, as a corollary, for any vibration which admits a section, we have that the previous one, Rudyak, Schumann, Murillo, and Scott TC, okay, coincide with or TC R, R. Moreover, when F is a vibration, okay, coincide with the TC R, R minus 1, and coincide with the Rudyak TC. Okay, good. Moreover, in the case when F is a vibration, okay, we obtain this standard estimate, okay. Recall, okay, this estimate, the lower bound is the estimate which present which happens for any map, okay. The upper bound is follows from the hypothesis that F is a vibration, okay, and recalling that definition of all hierarchies, okay. For example, okay, we recall that all hierarchy C, okay, in the case when F is a vibration, okay, we know this map R is it's easy to show that this is also a vibration, okay. The codomain is X r minus h s times y up h. Okay, this is a vibration. Okay, we obtain the classical estimate for this. This is the sectional number of this is less or equal the category of this product. Okay, for that reason we obtain this estimate. Okay, and this follows from the previous result. Okay, this is the method. Okay, and in particularly, okay, we have a refination, okay, of the monotonic hierarchy of Rudyak. Okay, and here for any vibration we have that or hierarchy r comma r is less or equal. This is by the monotonic property of RTC. Okay, this is more or less or equal r plus 1 comma r. Okay, and this is less or equal the r plus 1 hierarchy of the code. Okay, and moreover, when y is a h space, okay, this hierarchy C coincides with a category, and it is well known that this category coincides with the hierarchy C. Okay, good. And another estimate is, okay, it is very classical to obtain an estimate in terms of the cohomology theory. Okay, for our situation, we obtain an estimate. Okay, we consider a map, any map here, and any multiplicative cohomology theory. Okay, we have that or homotopy TC is more or equal than Nielsen index Nielsen of the kernel of this map. Okay, this map, okay, is this composition. Okay, where here is the diagonal map. Okay, and with the hypothesis that Kunet formula holds, okay, it is easy to show that the action of these homomorphisms in the cohomology in that product, okay, is as follows. Okay, we consider here elements in the cohomology in X and elements in the cohomology in Y. Okay, the action of these homomorphisms is, okay, here is the tensor product of them and is equal the copy product, okay, of this element. Okay, with this observation we can calculate, okay, we can compute, okay, some examples. Okay, and the first example is to compute this TC, okay, for this classical double covering map, okay, of the sphere over the real projective space. Okay, and this, okay, holds in this inequality. This hierarchy C is equal n times n plus this number, which depends, okay, this number accumulates two possibilities, okay, only this, okay. In contrast, when S equal R, it's easy to show that this epsilon R coincides with R. But for S less than R, happens two possibilities in general. Okay. For instance, when N is 1, 3, and 7, that means that this projective space is an ancient space. Okay. And using the previous result that this TC coincides with the category and the topological complexity, higher topological complexity one n space, we can show, okay, this TC is equal this. Okay, and we don't know at the moment, okay, that epsilon s less than r is equal to this. Okay. Okay. The prevision is that this happens for any s less than r. Okay. And obviously for any n different from 1, 3, and 7. Okay. But we have not approved for this situation. Okay. Okay. Now I will present, okay, the context of the motivations problems. Okay, it's easy to see that for that mechanical system, okay, it is modeling for this kinematic map. Okay, in the case for k equal 2, okay, and in the case when g equal to, okay, over the plane. Okay, but in for any p and any k, okay, we have this estimate. Okay, the or higher TC of this Fadel vibration, Fadel network vibration, okay, is less or equal the r minus s TC, okay, of this configuration space. Okay, here r minus s is at least 2. Okay, well, Gonzalez and Grant, okay, show that this TC is depend of the dimension of the parity of the dimension of the Phillips space, okay, and is equal of this in this case. Okay. Okay, so now I will compute the complexity of the initial and motivation cases, okay, and also I will present the algorithms, okay, the optimal algorithm for that situation, okay. Okay, and for the first case, okay, for the first case, okay, we have, okay, that the kinematic map for this situation, okay, is pi. Okay, we have here two objects, okay, for that reason, and the motion planning is over the plane, okay, and the motion is with a collision, okay. So the configuration of space of this mechanical system is F2, 2, okay, and the work mass is project over R. Okay, and the complexity of the motion planning or the motion problem for this mechanical system, okay, is easy to see that is the complexity of, in this case, okay, we have two intermediate states, okay, so we have with that TC R4 and S4, okay, of this pipe. Okay, this is the complexity for this situation. Okay, it's easy to find an algorithm. Okay, that algorithm, okay, need to move. Okay, I will this. Okay, that algorithm need to move this robot first. Okay, then go to R3, okay, then go to R4. Obviously, simultaneously, this obstacle move, okay? And it is easy to find a global algorithm, okay, which, okay, provides the route for this robot, okay? And for example, okay, note here that we are not interested in the initial position of the obstacles. Okay. Okay, we are not interested in that position. Only, okay, we know that these obstacles move over the plane, and we need to plan. Okay, I need to find a route for the robot, okay, which always avoid this obstacle. Okay, this is a mobile obstacle. Okay, here know that a motion for this induce a motion automatically for this problem. Okay, I will show this in GeoGebra. Okay, for example, a route for this. Okay, and let's get out here. Okay, here. Can you see these 2 points, A in blue and this red point? Yes.
Yes, yes.
Yes. Okay. I will start this algorithm, for example. Okay. I want to move this robot A for this position, then for this, and finally for this position here. Okay, and the algorithm gives, okay, a motion, a simultaneous motion of these two particular points, okay, without collision. Okay, but in the input of that algorithm, we do not incorporate the initial positions of this or the intermediate position of this obstacle, only for the robot. Okay. Okay, I will just some minute. Okay. Okay. I need to. Okay. Okay. For example, okay, this. Okay, for example, this is an example of that algorithm. Okay. Because in the input of that algorithm, we do not incorporate the position, the initial position of the obstacles and the final position of the obstacles and the intermediate position of that obstacle. Okay, for that reason, we can find, okay, a motion of this robot to satisfy, okay, that tasking. Okay, more to then here, then go to this, and finally go to this. Okay. In this case, okay, that route is this. Okay. This is the first time, the second period time, in the third period time. Okay. Similarly, you can see, okay, that similarly happens when in the algorithm we incorporate the initial position of the obstacle. Okay. Similarly, the same algorithms work. Okay. For that reason, the complexity, okay, for this, okay, in this case is 1. Okay, in the algorithm is given as I showed it then in GeoGebra. Okay, in the second case, okay, the complexity does not change. Okay, if in the input of the algorithm we incorporate the initial position of the obstacle. Okay, the complexity is again, okay, concise, okay, with 1. Okay, here, okay, the complexity of this situation is 4 and 3 of that projection. Okay, that concise again with 1. Okay. In the three situations, the complexity and does not is equal 1. Okay, in this case, in this case, we incorporate in the input of the algorithm the initial position of the obstacle and the robot, and one intermediate position of the obstacle and the robot, and then only the three intermediate position of the robot, and finally the ending position of the robot. Okay, in this case, the complexity for this mechanical system is TC4, 2. Okay, and we can show that this is concise with. Okay, now here, this in the plane or in any Euclidean space, is a particular example because, we are interested to move, this obstacle and this robot, starting in this position, in the first period of time, we need to move this obstacle to this position and this robot to this position. Okay, in this first period of time, you know that this is the TC. I'm sorry. Okay, this is the TC of F2, 2. Okay, in the first period of time. Then, we are not interested in the other position of the obstacle. For that reason, we can apply the algorithms. We can concatenate the global algorithm of the two previous examples. For that reason, this complexity only depends on the complexity of the domains of this vibration. Okay. An algorithm is easy to show this. In this situation. Only we need to recall how is the algorithm. For this configuration space. And also know that this configuration space is the topological complexity. This is homotopy equivalent to S1. And the topological complexity of this is 2. And an algorithm of this configuration space is as follows. And we want to move these two objects from this position and this for this without collision. In that case, we imagine we have this and S1, this sphere S1, and we compute this difference of these two positions from R1 minus O1. Take this vector R1 minus O1, and we normalize. In this case, we normalize this and give me this point in the S1. And we consider the antipodal of this point. This, the first step of this algorithm is as follows. We move this for this point linearly and move this for this point linearly. And similarly, I will, okay, identify or move these 2 points over the sphere, okay? Similarly, we need to take this difference, okay, here. This is R2 minus O2, and we normalize, okay? This gives me, the normalize gives me this point here, okay? This point here, okay? And we consider also the antipode, this, okay? And I will do this, okay? This object here, okay? And let's change the color. This for this, and the obstacles for this. Okay. We consider here in the inverse orientation. Okay. Okay. So in the sphere, okay, when 2 points are antipodal, okay, we use the vector fields of the sphere to find an algorithm. Okay. In this case, okay, we move these points in this sense, okay, and these points in this sense, okay. So if we concatenate of this path, okay, the obstacles move from O1 to this point, then move over this, and then move over this desired position. And simultaneously, the robot moves to this, okay, and moves to this simultaneously in the second part of the time, and the period of time, in the third period of the time, move to this. Okay, this is the one local algorithm for the sphere, is one of for the configuration. Okay, okay, this is a local algorithm for this configuration space. Okay. And then we concatenate, okay, with the other, with the global algorithm, okay, in that case, when we need to move these robots for this and for the final position, and you only are interested in the initial position of the obstacles, but for the other intermediate positions, you are not interested. Okay, for that reason, you can move this. I'm sorry. This position to this. Okay, and parallelly, this robot move. Okay, this approximately. Okay, this, and then, and finally, move this to this, and this. Okay, this is the one local algorithm, okay, for this situation. Okay, and similarly in this case, okay, now we can move these robots and these obstacles, but we ask that the obstacles and the robots pass, okay, through this intermediate position. Okay, R1, R2, O1, O2, then S2, S3, and then O2, O3. Okay, and then R4, but in the final position of the obstacle, we are not interested. Okay, we not incorporate that information in the algorithm. Okay, In that situation, okay, we can see that complexity of this problem, okay, is that topological complexity 4 and is 1, okay, of that projection, okay, and this coincides with the topological complexity TC3 of this configuration space F2, 2, which is Winkel 3. Okay, this has complexity 2. Okay, this is a concrete example in which I use all numerical invariants, okay, to resolve, okay, this kind of motion planning. Okay, okay, is on. Thank you very much.
Thank you very much. So are there any questions, please? Well, I do have one question, César. So in the very last part, you've been describing computations of this generalized version of topological complexity of Fadel Husseini's projections into, in a very concrete case, you're projecting only in one coordinate. So this is kind of the motivation for Farber and Weinberger and Cohen's parameterized TC, although it seems to me that the point of view is different in both situations. So I wonder if you have thought of the possible relation between this higher version of topological complexity of maps and higher versions of parameterized TC. And yeah, that would be the first question. Have you thought of possible relations? And the second would be, maybe if there are no relations, somehow it's because the point of views are different. But then it might be interesting to think that if there is a fiber-wise version of your higher TC for maps.
Okay, it is an they are nice questions, and for the first, I also thinking, okay, in that to relate the higher parameterized fiber and Cohen and complexity, okay. But for this higher TC RS, a natural, okay, connections. I am not sure now. Okay, I have not a sure answer for that question now. Okay, but I try to compare, okay, in a natural way, two higher this TC and the parameterized topological complexity. Okay, and now here, okay, in this situation for this vibration, okay, for this vibration here, okay, this happened. Easy to show that this happens for the open bow, okay, in the d-dimensional Euclidean space, but it's completely different when you consider the closed bow. Okay, for example, in that case, for example, only for example, in the simple situation when S equal R and S equal R minus 1, okay, all of them coincide equal 1, okay, for the Euclidean space and for the open bow, okay, the dimensional bow. However, when you consider the closed disk, that disease is not equal 1. Okay, I will write this. That TC, okay, for the case, we can consider here any R, okay, here is phi for the configuration space of the closed disk, d-dimensional closed disk, to project to this, okay. This is not 1, okay, for S R minus 1. Okay, does not happen in compare with the open board. The open board that coincides with 1 for S R and R minus. But for the closed disk, does not happen. Okay, because here is because this open disk have the fixed point property, and that implies that this vibration does not emit a clock session. Okay, and for that reason, in this situation, change for this open bow for the for this closed bow and for the open bow. Okay, and I will try to connect with the parameterized, okay? Okay, in the parameterized situations, I'm not sure, but if I think it's not depend of the open bow and the closed bow. Okay, so in this particular case, okay, is strong to compare that situation. Okay, only thinking in this case is R and R minus 1. Okay, and the projection of over the first current. Okay, but I have not a complete answer. Okay, to if there exists a natural connection with a parameterized Farber-Rudyak, or more general for the Farber-Rudyak case.
Okay.
Okay. Yes.
Okay, that's interesting. That's quite interesting. Any further questions?
Cesar, I have a question.
Yes.
Can you say anything in particular if F is the projection of a principal bundle?
Okay, yes, that is a good question. At the moment, I have not an answer, okay, a complete answer for that situation, okay. But I believe that we can obtain an estimate, okay, because I recalling in that case, when you consider a vibration over an H space, we have a complete answer for S R minus 1, okay? But for for a principal bundle, I believe that there is this kind of results in that same, but at the moment I have not a complete answer for that.
Okay, thank you.
Okay? That's a good question.
Okay, I'm going to stop the recording, but people can ask questions after that if they want.